nanohub.org.
Online simulation and more for nanotechnology.
My name is Erica Carlson, and I'm going to tell you about what I call the secret life of electrons in high-temperature superconductors. So I'll have to tell you what superconductors are, and then what high-temperature superconductors are. And to think about that, first thing we want to think about is, well, what makes things conduct in the first place? What a superconductor is it's some sort of conductor that's really good at it. It's super, okay? So we need to first think about what conductors are. So conductors are metals, and you know how to spot a metal, okay? You know what a metal is. A metal is something that when I put a voltage across the metal, electrons flow easily through the material. You can run a high current through a metal. Now, you don't have to do that experiment in order to show me where the metals are in this room. You can identify them just by the fact that they're shiny and they're smooth, okay? And they're malleable. You can bend them or you can beat them into shape, that sort of thing. And also they carry current. That's why we like metals, okay? They carry current, meaning they conduct electricity. And also when you touch them, right, if you touch a metal, it feels cool to the touch, typically, right? And that's not because it's colder than anything in its surrounding. It's because it's room temperature, okay, just like the rest of the objects in the room. But it has a high thermal conductivity. So when you touch the metal, it carries heat away from your fingers pretty quickly, and that makes it feel cool. So you could identify metals pretty easily. Now, metals are very useful to us. We use them all over the place to conduct electricity. But they still have a certain amount of resistance, okay? So when you were in high school, you probably drew circuit diagrams where you had actual resistors and capacitors in there, and then you pretended that the wires, the metal that connected those pieces, didn't have any resistance to it. But that's not actually true. Metals have resistance, and in fact, they have just a little bit of resistance, but it's enough to cause big problems. Wires radiate power away as heat, of course, okay? So if you were to feel of any of the wires in this room that are carrying electricity right now, right? The lights are working somehow, and the DVD projector is working somehow, and the computer is working somehow. So if you feel those wires that are carrying the current in, they're a little bit warm. If they're a little bit warm, it's because they're giving off heat. If they're giving off heat, it's because they're losing energy. And the reason they're losing energy is because when metals conduct electricity, they have a resistance to them, a finite resistance. So what this means is that all the wires we use, okay, that are metals, radiate power away as heat. So all over the power grid, all this power that's coming into the buildings and into our homes, they're just leaky pipes. We're always losing energy as that happens. So you pay for more electricity than you receive in your house or in your building. And what's going on inside the material is that what causes that is that the electrons have kind of sneaky ways to move around a lattice. Okay, but if they're moving around inside of a crystal, if the electrons are moving around inside of a material, as they do in a metal, and if one of those atoms is out of place, the electron can whack into the atom, and that's the way in which it loses some energy. Okay, it'll whack into the atom, give some energy to the atom that it just hit, and then the electron has to start again. So that'll happen either if the atom is just plain out of place and stuck there, or if the atom is wiggling too much due to thermal vibrations, which are always happening because we're always at a finite temperature. Now, superconductors carry electricity perfectly. Okay, so when they conduct electricity, they don't lose energy. And current in a superconductor, so if you take a loop of superconductor and you put a current in it, you just start it going and you just back away, okay? It'll just go forever. It's not going to decay. It runs forever. There's no resistance in a superconductor. So not only does it conduct electricity, but it does it perfectly, and the electrons never scatter off of the atoms inside that material. So that's pretty amazing. And I have to tell you what we mean by forever, right? What we mean by forever is the amount of time it typically takes a graduate student to graduate, okay? So they'll start their experiment, and then by the time they end their experiment, that current's still going. We count that as forever. Another huge property that's important for superconductors is how they interact with magnetic fields. So in fact, a superconductor doesn't just conduct electricity perfectly, it also expels magnetic fields in its vicinity. So It's even more severe than Lenz's law. So you know about Lenz's law. This is if I have a wire, just a metallic wire, and I bring a magnet towards it, the loop of wire will resist having the magnetic flux changed inside of it. So the wire will spontaneously start a current in the right direction to oppose that changing magnetic field. Superconductors do that, but they do it perfectly in the sense of even if there is a magnetic field to begin with, once the superconductor starts, completely expels the magnetic field from its insides. So the superconductor will turn on currents inside of itself, which it can do because it can do that without wasting any energy. Okay, so it spontaneously starts a current in order to expel the magnetic field from itself. So no magnetic fields allowed inside of a superconductor when it's in what's called the Meissner state. And this is not only technologically useful, but it can be pretty fun. This is an example of what's called the Meissner effect. The fact that when a superconductor is in its superconducting state, it expels magnetic fields. It can actually be a very strong force. This is Tosanumi, the sumo wrestler. These are Tosanumi's statistics. The total weight of Tosanumi plus what he's standing on right there is about 200 kilograms. And he's just standing on a disc with magnets. What's hidden under here are the superconductors. So there's a bunch of superconductors down here that are being cooled by liquid nitrogen to keep them cold enough to superconduct. And there's a little gap of air in here. So the fact that the superconductors are cold enough to superconduct, once they do that, they expel the magnetic fields, which means they repel that magnet that Tosanumi is standing on. So that's a pretty good effect, right? Big enough to hold up Tosanumi, the sumo wrestler. So people have hopes that we might be able to use this in, say, levitating trains, for example, to have a train run basically frictionlessly, because it would be levitating. So the question is, how does this work, right? How in the world is a superconductor able to do things like that? How does it superconduct, meaning how does it conduct electricity without losing any energy? So first I have to ask you a question, okay? It's a room full of science students. Can two pieces of matter occupy the same space at the same time? People look at me like this is a trick question. It is, but that's okay. Play along. Can two pieces of matter occupy the same space at the same time? Are you currently falling through your chair or sitting in it? Okay, so we're taught that two pieces of matter cannot occupy the same space at the same time. This is why when you sit in your chair, you sit in it rather than falling through it. This is why when I stand on the floor, I stand on it rather than falling through the floor. And this is why when I clap my hands, I can actually clap rather than having them just pass right through each other. Okay? So no two pieces of matter can occupy the same spot at the same time, but it turns out that's only half true. There are two kinds of particles in the world. We categorize them as fermions and bosons. So fermions are the stuff you're probably more familiar with because we're made of fermions. Fermions are things like protons and neutrons and electrons. Things that have, if you are familiar with the quantum mechanics, they have what's called spin a half. They have a particular amount of intrinsic angular momentum, which we call spin, and the amount of spin, intrinsic angular momentum that they have, it comes in half numbers. So if it's spin a half, spin 3 halves, spin 5 halves, it's categorized as a fermion, and electrons, neutrons, and protons follow that. And that's what we're made of. So that's why we can't pass our hands through each other, okay? You might say, well, the real reason I can't pass my hands through each other is because of the Coulomb repulsion, right? I mean, ultimately, the outside edge of my fingers is composed of electrons, and the electrons repel. But if it were just a question of Coulomb repulsion, if it were just a question of the electrons are negatively charged and they repel each other, then I could potentially push my hands together hard enough and get them to go through each other, okay? So this is far more severe than that. This is quantum mechanically forbidden for electrons to be in the same spot at the same time because they're fermions. So fermions obey the Pauli exclusion principle, and in fact, you were taught that already in high school chemistry when they taught you about putting electrons inside of an atom, and they said, okay, you have the 1s state, you have the 2s state, and the way you're going to fill up those electronic energy levels inside the atom is you'll put a spin up electron in the 1s state, and then you'll put a spin down electron there. And then you'll go to the next state. When it's time to put the next electron in, it can't be in the same state. It can't be in the 1s up or the 1s down state, those are taken. So you have to go to the 2s state. Okay, that's the Pauli exclusion principle, and that's that idea that it's quantum mechanically forbidden for two electrons to do the exact same thing at the same time, such as sit on top of each other. So that's fermions. Bosons are totally different, okay? Bosons have spin 0 or spin 1 or spin 2, and they are allowed to occupy the same space at the same time. So you actually have experience with bosons. Photons are bosons. So particles of light are bosons. And this is why, for example, a laser pointer works. Okay, the reason a laser pointer works is because you can pump a particular electromagnetic mode, meaning you can put a lot of photons all in the exact same state and get yourself what's called a coherent electromagnetic wave. That's what a laser is. And so that very high intensity is because you've got a lot of photons all doing exactly the same thing at the same time. And that's because they're bosons. They can do the exact same thing at the same time. Do you have any questions so far? Okay? All right, you with me? There's fermions, there's bosons. We're made of the fermions. Okay, all right. So, electrons are fermions. Okay? They obey the Pauli exclusion principle. And of course, you know, if you had Club Pauli, the Pauli exclusion principle, you get one fermion in, that's it. Club's full, okay? The bouncer is going to be turning everybody else away from Club Pauli. And this is why most matter can't occupy the same space at the same time. Bosons are allowed to occupy the same space at the same time. You're used to this with lasers. Photons in lasers are occupying the same quantum state at the same time. Also, superfluids do this. So if you've heard of superfluids, they have very strange properties because they're made of bosons. So the helium-4 atom is a boson. When you consider it all together, yes, it's made of electrons, neutrons, and protons. But if I put an even number of electrons, protons, and neutrons together, the whole composite particle is now a boson. And that's because we count the total spin by the spin of halves. So if I had, 2 protons and 2 electrons, then I add up all those spins and I would get an integral number there. And so that helium atom then is a boson. So helium atoms, if you get them cold enough, they can all go into the same quantum state. They're allowed to. And that's what causes a superfluid. And superfluids do very, very strange things. For example, not only do they have no viscosity, but they can escape their container. So if you leave them, so if you have a superfluid at home, keep its lid on. I mean, otherwise it's just going to come out of its container and eke away. I'm sure this has happened to everybody, right? Your superfluid, you left the top off and you came back and it's gone. The main property of a superfluid that's technologically interesting is that they don't have viscosity. So viscosity is like if I have a bowl of water and I stir it up with my finger, I can feel the water, okay, resisting me. And the faster I stir, the more I feel the water resisting. If I do that with a bowl of honey, try to stir the honey up really fast, it's even harder to stir, it's more viscous. If you do it with a superfluid, you won't even feel it. Okay? No viscosity, no resistance. You just be like, what? There's nothing, it won't feel like there's something there, except for the fact that it's really cold. So don't do that unless you have a glove on. Got it? Okay. All right. Now, the trick is that, Bose condensation is what allows these bosons to go sit in the same quantum state at the same time. So superfluidity does this. And so bosons have this very special property in that they can sit in the same quantum state at the same time. They're not only allowed to do that, they really like to do that. So if I have a collection of bosons, okay, bosonic particles, and I lower the temperature on them, they'll all go to the lowest state available, and they're all allowed to crowd into the lowest state. And in fact, they really like to do that. And once they get to the very lowest state, it's actually very hard to get them back out again. They're kind of a little bit sticky. Okay, once they get there, they tend to stay together. And that ends up being a very, very stable quantum state. It's what leads to what we call the dissipationless flow of a superfluid, or the zero viscosity of a superfluid. It's also going to be the key to getting, the superconductor to superconduct. Okay? And we do think that most metals at low enough temperature eventually superconduct. So let me tell you how in the world you might get some bosons out of a a material that's made up of protons, neutrons, and electrons. So think about a metal. Let's think about a regular metal. And what happens inside of a regular metal, if you get it cold enough, it eventually superconducts, okay? Now, I say that, and we think it's true, okay? In cases where the metal doesn't superconduct, where we take it down to the lowest temperatures, we just think that probably if we took it to lower temperatures, it would eventually superconduct. But our belief is that all metals eventually superconduct at low enough temperatures. And so what happens is that the electrons form pairs, and then those pairs are bosons. And then the bosons themselves, the pair of electrons, since it's called a boson, can now go into the same quantum state. And at the very lowest temperatures, they'll all go to the very lowest energy state, and now they're very stable. Now, why does this lead to no resistance in your superconductor? If I think about what is it that gave me resistance in a regular metal? What gave me resistance in a regular metal is that the electron that's carrying current in a metal would be traveling along, and believe it or not, electrons know how to skip all the atoms, okay? If I just take a material and the atoms inside the material are regularly spaced as they are in a metal, it's called a lattice, okay? So the atoms are regularly spaced. The electron can look out over that and say, I know exactly where all the atoms are. They're all with this particular periodicity, and the electron basically surfs through at the right frequency. Okay, it just gives itself the right wavelength to surf through, and it misses all the atoms. The only problem is if an atom is out of place. So if an atom is out of place, then when the electron's coming along, it wanted to, it was intending to miss the atom, but the atom's out of place, so it can whack into it. When it whacks into it, it gives off some energy, and the energy goes to the atom that it just hit. Now, for this to happen, as the electron's coming along, if it's going to hit that atom that's out of place, what happens to the electron? Okay, it had some energy, it whacks into the atom, it loses some energy, which means after the collision, the electron is in a lower energy state. Does that make sense? If the electron loses energy, after the collision, it must be in a lower energy state. That means there must have been a lower energy state for the electron to go into. So what would happen, okay, if I had an electron that was in such a low energy state, it was in the absolutely lowest energy state, and when it got to that atom that was out of place, there was no lower energy state for it to go into. What would happen in that case? Right? In that case, if there's no place for the electron to go after the collision, it actually cannot collide. Okay? And this is what happens when we have the case of a superconductor. In the case of a superconductor, the electrons pair. The pairs are bosons. Bosons are allowed to all be in the same quantum mechanical state at the same time. So I lower the temperature on that system. All the bosonic pairs of electrons are in the very lowest energy state possible. And then, if that pair comes along and gets to a misplaced atom inside of the superconductor, it actually can't lose energy because it's already in the lowest energy state, right? So if it's already in the lowest energy state moving along, it can't lose energy through that collision, which actually means, in fact, it's quantum mechanically forbidden to knock into the atom. Okay? That's really strange, but that's quantum mechanics, and once you learn quantum mechanics, you just get used to things being strange, okay? So the electrons, when they're paired as bosons, and they're already in the lowest energy state, cannot scatter off of a misplaced atom because they can't lose any energy. They're already in the lowest energy state. Therefore, there can't be any resistance in a superconductor. Did you follow that? Okay, so that's why superconductors don't lose energy as they conduct electricity. Those paired electrons just zoom through the material and don't bump into anything and don't give off energy. Now, we have known about superconductors since 1911 when it was discovered that mercury superconducts. And this is a chart of over time, these are years, not to scale, and then the highest transition temperature we know about, okay? So mercury is a very, very cold superconductor. It goes around 4 Kelvin, is the temperature at which mercury eventually becomes a superconductor and loses its resistance. And then as time marched on, we found other materials that superconduct, and we would find, for example, here in the 30s is when the niobium compounds were discovered, and we eventually got superconductors that could superconduct up above 20 Kelvin, but not too far above 20 Kelvin. Even in 1970, we only went up to about 25 Kelvin. And then there's this gap in the discovery chain. There was a long time period there between 1970 and 1986, so about 16 years, where nobody's discovering a higher temperature superconductor. Okay, so for a long time we were just kind of stuck, and we knew of superconductors, but we never could get them to work at very high temperatures, only up to about 25 Kelvin. This is a great period in materials science, okay, and in materials physics, because this is a time period when a lot of people start writing papers about how superconductivity will never work above 30 Kelvin, and why it will never work above 30 Kelvin. And, I know somebody who's a very successful physicist who wrote her PhD dissertation about why it's impossible for superconductors to work at above 30 Kelvin, okay? Didn't hurt her career. She's good physicist. And see, her dissertation advisor talked her into it, and he has a Nobel Prize. So, you tend to believe these people, right? So there's this great time period there when we thought superconductors couldn't work above 30 Kelvin. And then there was 1986. All of a sudden, there was a new family of materials discovered, the cuprate superconductors. So these have copper, oxygen, and other stuff in them. And it was discovered to work at 38 Kelvin. Amazing. And then, very quickly afterwards, a similar family, the yttrium, barium, copper, oxygen materials were found to superconduct at 92 Kelvin, and then it kept marching on. So right now we can go to about 160 Kelvin under pressure in that set of materials. So there's clearly something totally different going on in these guys. They're a new class of materials, and they were a surprise because we do understand how regular metals superconduct. Regular metals, if you get them cold enough, will eventually have their electrons pair. Then those pairs can Bose condense, okay? And then you get the superconductivity. These materials were a total shock. They're not metallic, the new ones, the new cuprate high temperature superconductors. They're not metals. They don't even start off conducting at all. That's a picture of one, and I'm going to start passing some around. They're ceramics, okay? Ceramic as in ceramic like the plates you eat off of. Not right now, you're eating pizza off of paper plates, but when at home, presumably you have some ceramic plates. So I'll just pass some of these out, and you can feel them yourself. They're ceramic. This is a high temperature superconductor. It'll superconduct when we stick it in liquid nitrogen. Got some little pieces here. And you can feel it. It's black, okay? It's not shiny, okay? It's ceramic. It's brittle. That's why it's broken into many pieces, is because I've passed this out many times before, and it started as a uniform disc, but it got dropped on the floor various times. So if you drop it on the floor, it breaks. If you step on it, it crushes. It's ceramic, just like a ceramic plate. And it's definitely not metallic. And in fact, if you tested its conductivity right now, it's rather low. So this is definitely not a metal, right? Everybody can just see this is not a metal. It's black. It's not shiny. And when you touch it, does it feel cool to the touch? No, right? Not like a metal. Metals are cool to the touch, and these guys aren't. So, and, there's magnetism inside this thing. Right now, there's little, atomic, magnetic moments that are inside this material, and that's strange because superconductors typically, as we said, expel magnetic fields. So these have magnetism intrinsic to them. Plus, just so you know, you can make your own. It's been turned into a high school chemistry experiment. There's the recipe right there. You just need the right materials in a really hot oven. Okay? But basically, they're pretty robust materials in the sense of, like I was saying, it's been turned into a high school chemistry experiment. So you just you stir it up, you crush up the materials and stir them up into a nice fine powder, and then bake it at a really high temperature, and out comes something that actually superconducts. So it's not all that sophisticated to actually make one. And yet, okay, so we've known about these things since 1986. We don't know how they work, okay? Now, I say we don't know how they work. I know how they work, okay? I write about it. It's what I do research on. But a lot of other people in the field also know how they work, and we don't agree, okay? So that's what scientific progress is about, is that there's a lot of different ideas about how these guys work, and nothing is agreed upon yet, okay? There's not consensus in the field. The experiments haven't unambiguously said it's this idea and it's not that idea. So there are a lot of ideas about how they work, but there's no agreement on it yet as to how they work. So this is just to give you a sense of they are complicated chemically. Okay, even though you can make them just by crushing them into a fine powder and baking them, they actually are much more complicated than a simple metal. You know, a simple metal that superconducts at low temperature can be a single atom, right? And that, you know, that would be the composition of it. These guys are complicated chemically. This is just to show you pictures of the unit cells of them, just to emphasize that there's a lot of important chemistry going on inside of the materials, and there's various families of them. This stands for yttrium, barium, copper, oxygen. This stands for lanthanum, strontium, copper, oxygen. Here we have mercury, copper, oxygen. And what's common to them is that they all have copper oxygen planes in them. So there's families of these high temperature, cuprate high temperature superconductors, and they have a copper oxygen plane. And then there's other stuff in between that gives you the different families, whether it's the lanthanum family would have lanthanum and strontium in here. The bismuth family would have bismuth and calcium and strontium in here, and so forth. Part of what we think is probably going on inside these guys, just to give you a taste of, well, what kind of work do I personally do on these? We think that the correlations inside the material tend to drive the electrons into spontaneously striped states. So that is, they tend to go into little rivers of charge. And why would a river happen? Well, why would a river be interesting? Anytime you get kind of complicated interactions among particles, you can get little rivers forming. Okay, these are examples of other systems that do the same thing. They'll have some sort of competing interaction in them that leads to these little one-dimensional channels inside the material. But I think what's interesting is you know, what is it that's so special about one dimensions? Okay, so if we think that maybe inside this material, the electron-electron interactions drive the electrons into little rivers of charge, that's neat. Okay, so now we can get the electrons to go more or less in one direction. What's so special about one dimension is that physics is very different depending on the dimension that things are in. So if I think about, for example, what happens to waves in various dimensions, waves in various dimensions behave very differently. And we think that's part of what's going on in these guys is that the electron waves themselves, because they travel one-dimensionally, are fundamentally different in character and give you something fundamentally different and new, which gives rise to the high-temperature superconductivity. So if you ask me about that later, it would take me maybe 20 or 30 minutes to explain to you what all that entails. But let me give you just a taste, okay, of why it is that we think that if electrons go into little one-dimensional rivers, that might be a very exciting and different thing going on in the material that can lead to high-temperature superconductivity. So think about waves in various dimensions. So right now you're listening to my voice. My voice is being carried by sound waves. The sound waves are going out in 3 dimensions because we're in a 3-dimensional space, okay? Now, the energy, the power basically coming out of my voice dissipates, okay, such that you guys in the back can hear me. But, in fact, if we made this room larger and larger and larger, I'd have to talk a lot louder for the people in the back to hear. That's because the power in the intensity coming out of my voice gets distributed over the whole room. So if you think about the sound waves radiating out from me, they radiate out like a sphere. And then the energy from that gets distributed over the surface area of the sphere. The surface area goes like 4 pi r squared, right? So then all that energy gets distributed over r squared. So then it dissipates. The energy then dissipates as 1 over r squared. That is what comes to your ears, okay, the intensity is down by 1 over r squared, where r is the distance between me and you. That's why sound waves die off in intensity as they travel. It's different if you throw a stone into a pond. Anybody ever thrown a stone into a pond? Yes, okay. So think of water. Now we've got a 2-dimensional surface and we're going to make a 2-dimensional wave. I throw a stone into a pond. It makes little ripples that go out on the surface, but the ripples aren't spheres. The ripples are circles, okay? So the energy of the wave gets distributed over the circle. The circle, how big is the circle? That goes like R, right? The radius of the circle. And so the energy then gets spread out over the whole circumference of the circle, which goes like r, the radius of the circle. So then as the circle gets bigger and bigger, the wave actually dies out like 1 over r, 1 over the radius of the circle. You following me so far? The waves basically are different in different dimensions. Now, one dimension is going to be totally different. So now think about something in one dimension, okay? Maybe think about a canal or something like that, or just a string. And think about a disturbance in that one-dimensional system, in that river, for example. And where's the energy going to go, right? It can't do what happens in 3 dimensions where it spreads out all over the sphere. Can't do what happens in the 2-dimensional surface of the pond where it spreads out over the circle. It just goes, right? So if I have a disturbance in one dimension, it just keeps going. It can't turn to the right. It can't turn to the left. There's just one way to go. So in fact, in one dimension, waves don't dissipate. That leads to what's called solitons. Okay, maybe you've heard of a soliton wave. They were first discovered on a canal. Long time ago in the 1800s, John Scott Russell, a canal engineer, noticed that the wave in front of a boat in a canal, once the boat stopped, the wave kept going. And he thought, well, that's kind of strange. It seems to be not changing. The wave seemed to not change. So he got on his horse and he followed this wave for a couple of miles before he lost it. And he observed that it just it kept its shape and it kept its speed. It did not dissipate. So waves in one dimension are fundamentally different, which is why we think that if inside of this material the electrons go into little one-dimensional rivers of charge, that gives you something fundamentally different from the other types of superconductors and can give you a route to the high-temperature superconductivity. But that's just a taste of that. So if you have more questions about that, please ask me afterwards. So now what I want to do is I want to have you do the superconductivity demonstration yourself. So we're going to pass out these little pellets of superconductivity. You all have little fragments right now, but I'm just going to go ahead and pass out the whole kit to you. And then I'll bring around some liquid nitrogen. Okay, and this is the part you're working on, is levitating Tosanumi, the sumo wrestler. I spin it, but yeah, isn't that neat? So that just shows you how frictionless they can be. I mean,
I think I've seen a video of this on like 69 symbols.
Totally amazing.
Really cool.